replace it with your average homework.
Oh, look at it.
Is he doing it without the lowest homework or with the lowest homework?
Oh, good question. Benevolent versus malevolent.
I never said that.
That's the difference. I'm giving out stickers.
I'm just there, so. I'll take a sticker.
Yeah, but you
Right.
still have to run the risk every single day because he doesn't take your name out.
That is also true.
Yeah.
Yeah, it could be your name 5 times, and
Yeah.
if you're not there the 5th time,
Yeah.
suck it.
Yeah.
Yeah, you're out.
The first 4, but it's like you forgot to email the 5th.
Yep. So we talked about moment curvature, right? Starts out, right? This is just a standard beam with an eccentric pre-stressing strand. You start out right at the very beginning. The thing is actually curving up, so it has negative curvature when there's no moment applied. We're going to apply a little bit of moment to it, just a self-weight, and we'll have a condition where everything still is in compression, right? You get more compression down at the bottom and less at the top, and that's because of this offset thing. It still has some negative curvature still being applied up. You apply even more moment, and at some point the internal moment and the external moment cancel each other out, and you have this balanced condition where you just have a uniform compression force. That's just gonna be F over A. It's just F over A. We'll see the equation here today. Keep applying load, you'll get to a point where you decompress the bottom, right? The bottom is compressed, but you get to a point where you apply enough external moment, enough downward moment or load to then cause this bottom right here to become uncompressed, right? Decompressed. And some codes, we'll talk about this later, about certain, depending where you're at, that's gonna be a design criteria. Is what do we use for our allowable tension stress? Some scenarios, some state DOTs say you can't have any tension anywhere on your beam. And so what's gonna control is this guy, is this 0 down at the bottom. Other states allow some, right, tension, right? So you keep applying load and you'll get a little bit of tension down at the bottom. And then as you keep applying load, then, all sorts of stuff starts happening. Your concrete becomes nonlinear. It cracks from here up to here. So everything from here to here is above this rupture strength of your concrete. So it's cracked all the way up to that point. And you keep applying a load and you get to this over here where it's the ultimate load. We still do ultimate load, but this is just gonna be a check afterwards. We're gonna live in this range right here, right, when we do our designs. Okay, and then you also have some limits. So we'll get to these, but you're gonna have some limits on tension stress, and you're also gonna have some limits on compression stress. We gotta make sure that in this state down here, we don't go above the compression limits, and up here, we have to make sure we don't go above the compression limits, and we gotta make sure we're, stay within the tension limits throughout as well, but we'll get into that. Okay, so briefly, we talked about what gets complicated about pre-stress design is all of the load stages that we have to check for design, because different things are gonna control under different circumstances. So I gotta get notes. Okay, so under jacking, this is important, right? This is when you first load up the tendons, right? This is gonna be critical to the tendons. And this is the most load that the tendons are gonna see. Okay. Either post-tension and pre-tensioning, right? It's going to be the most of those tendons see. So if you're going to get a rupture of one of your tendons, this is when it's going to happen, right? Because you're pulling on it, and then so pre-stretching, pre-tensioning, you stretch it out, cast the concrete, and release it. Once you release it, right, it shortens, and so then we get some immediate losses in the tendons. And so there's going to be some limits on how close. You can't pull your tendons up to 270 KSI. You get in a range of 270, but you can't go all the way to 270 because the shit might break. Okay, and they do break, which is scary. Okay, so then the next stage that we care about is the initial stage. We denote it with a little I floating around, and that has to do with at the transfer, when we're transferring the loads from the tendons into the post-tensioning. Okay, is when our beam is very young at this point, right? The concrete is green, right? We don't have, we just have the self-weight of the structure on it. Oh yeah, concrete is green, right? Self-weight of the structure, or the element, is the only thing that it's carrying at this point. And no service loads. Just right at the very beginning, and you're really careful with it. Okay. No losses. Major pre-stress losses beyond elastic. And there will be some elastic pre-stress losses that happen right away. Right? In pre-tensioning, you pull it out, cast the concrete, release it. Well, it's going to squish the concrete and it's going to shorten a little bit, and you're going to lose that. But we're not doing no long-term pre-stress losses at this point. Okay, and so when we use these calculations, we have to be using the right variables in this. Okay, where we're going to run into issues is compression bottom, tension top. Right, and that's standard. Keep in mind, these are all standard beams, right? Simply supported beams. That's what we care about. Compression bottom, tension top. So it's curving up. That's why I have this drawn over here on the right. Is it's curving up, right? At this initial stage, with an offset pre-stressing, it pops up, right? And when it pops up, we got to make sure it doesn't crack up here and doesn't run into compression down here at the bottom. And then when we use our concrete materials and our steel materials, we have to use the right ones. And the ones that we're going to have to use, we'll write the equations a little bit. We're going to use FPI, which is the pre-stressing force at the initial without the pre-stress losses. Right? Initial before losses, right? And then, I'm running out of room here. Oh, there we go. And then we're going to have also F prime CI. We're going to use the initial concrete strength, the 7-day strength or whatever it is, that when we release the load on it, not using the 28-day strength. And then also same thing with FTI. Right? Our initial tension, allowable tension stress in our concrete. We'll define what F prime CI and FTI are later. They come from the ACI code. Okay. Then we get into the effective service loads, right? And this can control design. Right? These can control design. It's worth noting because it's kind of weird to think about it. We'll get into that a little bit later. But basically, you want to put these tendons, right? The best place to put your tendons are down at the bottom, right? Because you want to cancel out the external load. So you put them down at the bottom, right? But if you put them too far down at the bottom, then you're going to run into problems. That's where you're going to end up with tension at the top and compression down at the bottom. You're going to run into issues there, right? So if you put them down really far. And so then you're going to have to put them up a little ways. You're going to have to raise them up a little bit or decrease the pre-stressing forces so that you don't run into this issue right here where you get compression at the bottom and tension up at the top. That can control design. Effective service load. Tommy Malott was cut.
I saw.
What the hell? What?
He got waived.
He got waived because it went to 72 to 53. Is how it happens, and he got hung up with
I
that.
think they do practice squads today.
Oh, and so he's out. You know what he's doing? Any word on what he's going to do next? Does he hopefully get picked up by someone else? Is that how that works?
Yeah, they have their practice squads. They signed those guys today.
So
Oh, he might make the practice squad.
Any team.
Oh, that's too bad. I wanted to know someone famous. I don't know him though. I don't.
I wanted to get him a Lot Raiders jersey.
Oh yeah. Oh, you still can.
Make the 53.
Oh, you talking shit, Kyle.
Before I spend $200 on a jersey, yeah.
Yeah. Is that how much a jersey costs?
They're crazy now. It's like I looked and it was like 160.
Oh wow.
That's too much.
Concrete's full stick. So effective service loads, right? This is, and that's denoted with a little subscript E, right? In this case, right, now this thing, before you put real loads on it, we're gonna wait for the concrete to come to strength, right? And usually when we talk about full strength, we're talking 28-day strength. So our concrete has come to strength. So we're gonna use the full concrete strength. Right? Full dead loads and live loads. All right, including the self weight, right? Just the total load. and we'll keep going with this. I'll say, live load is complicated. We'll get into that. So there's different limits for different live loads. There's permanent live loads, and there's temporary live loads, and so it's going to be dependent upon that. Just to make note, live load. God dang. Okay, fair enough. And then what else do I say about this? Oh, this is going to be the opposite, right? We're going to have full pre-stress losses. Right? At this point, we're going to assume that we've lost the concrete has creeped. We're going to make this assumption that the concrete has creeped. We've had any relaxation in our steel, right? And we're going to reduce what our pre-stressing forces are. They're going to be less pre-stressing forces at this point. You're going to run into problems. This is going to be the opposite. We're going to have tension at bottom and compression at top. Right? Those external loads are bigger now. They're going to overpower the internal loads, and we're going to get a regular positive curvature, which is bending down. And then we're going to use FPE. That's after losses. That's our full pre-stressing force after losses. After losses. This is going to be, and then we'll also use F prime C. No I on it. And FT. No I on it. Sometimes you see an E afterwards. We'll see. We'll get into a little bit. Right, so you can see when we go to the design, like I said, it's very simple design equations, which we'll formulate shortly. Right? But then where it gets complicated is we're going to have to check. We're going to use different properties, right? We're going to use, sometimes when we're checking the initial transfer, we got to make sure we're using this allowable stress, this allowable stress. We're using FPI instead of FPE, and we're worried about compression here and tension here. Then we're going to go on, we're going to check the effective service load, right? And at that point, we're going to use the one with the full pre-stress losses. We use our full concrete strength and our full tensile strength when we're doing our design. All right. Okay, so before we dive in, we're going to use the sign convention. You're going to like the sign convention because we're just going to be able to get away with using one equation for our calculations. Okay, and this is what Stanton does, so we're going to stick with what he does. Right, so this allows for one equation for the top and bottom, and if you pick up an old pre-stressing textbook, they'll have two different equations, one for the top and one for the bottom, right? And then the positives and negatives change. Okay, and then it helps for automating the process, right? We're going to have an Excel spreadsheet or a MATLAB program that's going to do a lot of this stuff for us, right? And it helps us automate it, and it keeps track of what's in compression and what's in tension, and it actually is really slick. Okay, so the first thing we have to do is define that. First of all, there's a full article from, I think it's PCI magazine, written by John Stanton. I put it on the Canvas webpage that has this thing written up if you want to look at it. It's got a nice little description. He has some examples and stuff in there as well. Also, the Canvas, I assigned a homework. Do you guys get notifications when I assign a homework? Yeah, I think you would have, but I had all the homeworks in there already, and so when I edit them, it doesn't kick it out to you as being something new. So if you look under assignments in Canvas, there is an assignment due next Friday. So there's some time, but just take a look at it. And it's a little PDF that has, problem 1 is doing a bunch of reading, problem 2 is just doing calculations on this stuff. We haven't really quite got far enough yet anyway, but so by next Friday, make sure you look at that. And then we're going to turn it in through Gradescope, which is linked to Canvas, but only if you're not using Safari. But it doesn't matter if you're using Safari. You can just go open up Gradescope and it'll be there, and you can submit it that way. You don't have to go linking it through Canvas. It'll be in your regular Gradescope location. Okay. Oh shit! I left part out. Let me add one other thing. I'm gonna add a D. Ultimate loads. I wasn't finished yet. That's right. God, I've forgotten to do that. I'm really upset with myself. I just don't make any mistakes anymore. So it doesn't happen. Right? In this case, we're going to use factored loads. Right? Chances of people dying, we're going to pretend our loads are bigger than they actually are. Okay? And we're going to do nonlinear analysis. Right? Which involves the Whitney stress block, cracking, etc. Right? Full on deal. But I want to make it's worth mentioning that is actually a load stage that we have to take into consideration. Is even beyond effective service loads. Because we care. We care that people die or don't die. Okay. Design convention. Some key components here. So this is, I hate to tell you this. I mean, for the most part, I'm just going to give it to you. But this is a section, right? If I wanted to figure out what the moment of inertia of this section is, what would I do? Well, I made it up. It's concrete. It's made up, right? What do you have to do this? Or it's like unusual parallel axis theory, right? It might come back into play. I think for the most, I don't think I might do one problem where you have to do it. I don't remember. Otherwise, I'll just give it to you, okay? But eyes matter now, right? When you're doing regular concrete design, eyes go away, right? Because everything, we go right in regular concrete design, we go right to this ultimate loads, nonlinear analysis, and then moments of inertia don't matter. Now though, like when we're doing this, we're in the elastic range, it's the service condition, okay? And everything's remaining elastic, and my over I is the equation we're gonna use. We're gonna need to know what the moments of inertia are. We're not gonna calculate it for this, but just you might have to do it. And you would know how to do it. You just look it up. You can look up how to do it. You can look up how to do it, but maybe not. Okay, so this is our deal. All right, so some of these rules of this system is, one of the ways for the sign convention is we're going to define something that's called the CGC. Center of gravity of the concrete. That's what the CGC stands for. Center of gravity of concrete. Okay, so you'd have to find that center of gravity, right, if it's not given to you. Okay, in this particular problem, right, the CGC will be offset. I'll tell you what it is. We won't actually calculate it. CGC will be up here. Well, you got a new thing. I can go like this. Right, it was on here. Well, it is raining. CGC, center of gravity of concrete. You're going to have to calculate where that's at, right? Because all of your bending that's happening, right, from the pre-stressing and from the external loads, it's happening about the center of gravity of the concrete, right? That's where everything that's where everything bends about, is that CGC. Ultimate load's not the case, but for this, it is the case. Okay.
How is that different from the neutral axis?
Same. Neutral axis and center of gravity is the same in this case. Where they don't align is when things go nonlinear, right? When things go nonlinear, things get weird, right? That's where you have to figure out where your compression block is at, your A, by setting the C equal to the T, and it solves that. They don't align then in the nonlinear range. In this, though, they align. Yep. Kind of, because the neutral axis means it doesn't move at all, okay? But we're pre-stressing this thing, so everything moves. Everything. So there's not really a neutral axis at all. That's confusing as hell, right? But there isn't. If you think about it, right, you've pre-stressed it, so it has a pre-compression, so everything moves. There is no spot that doesn't move. But all the bending that happens will happen about the CGC, which would be your neutral axis if the pre-stressing force wasn't there. I think that does okay. Makes sense to me. That's all that matters, right? Okay, CGC, right? Y's, right? So this is going to come into play, right? Y's are the distance from the neutral axis to whatever you're looking for, right? Or wherever you're looking for, my stress is at. Y's and C's are measured positive down negative, up. Right? So sometimes you see as my over I or mc over I, right, as being our stresses. Y is just any location along the height. C's are the extremes, is what they are. But they get interchanged quite a bit. My and mc over I kind of get exchanged, right? So the Y's and C's are measured positive down, negative up. So if I'm up here at the CGC, and I was saying, you know, my C, right, would be the distance between here and here if I'm going that way, and or C would be going this direction, depending on if I'm looking at the stresses down at the bottom or looking at the stresses up at the top. But if I put them in, so the C's and Y's are going to carry a sign with them. So if I go this direction, right, if I go that direction, it's positive. If I go this direction, it's going to be negative. Right? So if I'm going to have a negative C if I'm talking about the top, and I'm going to have a positive C if I go down to the bottom. Right? And there's reasons for this. It kind of, like I said, once we get this, as long as we stick to this sign convention, it just makes our lives a lot easier. Okay? And this is what Stanton does throughout his notes, so we're just going to stick with what he does. All right, bottom, we're going to call 1. Top, I'm going to call 2. And CGC, we're going to call 0. Okay, and there's some reasons. Oh, man. When I said CGC, it thought I said Siri, and then it made a phone call to someone. So I don't know. I don't know who I just called. Right? And you were like, well, why don't we call bottom B, top T, and then CGC C? Well, because there's another C floating around already, and there's already a T floating around already. And so if we did that, then it gets, and also Stanton does it this way, as we're going to stick with the way Stanton does it in his notes, okay? There's some reasons for doing the 1, 2, and 3. It gets confusing as hell later on, but I go, 2 starts with a T, it's the top. 1 doesn't start with a, starts with an O, and there's an O in bottom. And then, yeah. I don't know. It's one of those things. So if we're talking about something that's happened up at the top, we call that 2, right? And then this will be 0, right? And then down here, we'll call 1. Right? And so it's like, we're talking F1, we mean the stress down at the bottom. I think historically students oftentimes they just spell it out. It's easier to do it. F top, F bot, right? FC, CGC or something like that. You can just spell it out too if you want. That maybe is a little bit clearer to do it that way. But his notes and stuff like that use this sign convention and call those things. Okay, so another comment here. We'll do an example and kind of show you what the benefits of it. Section properties carry signs. Right? So even powered properties are always positive. Right? Things that are even powered or area, right? Inches squared, right? And so when you square your dimensions and stuff, A is going to be an even power, inches squared. I's will also be, right, inches to the 4th. Those will always be positive. But odd powered can be positive or negative. Okay? They can be, right? Just depends on what they are, right? Depends on if I'm going up or if I'm going down, right? If I'm going up, they'll be negative. They'll have negative section properties. If you're going down, they'll be positive section properties, right? Right? Examples of evens would be C, Y, and then obviously S, which is dependent upon C and Y. Right? C is S is inches to the 3rd, C is inches, Y is inches. So those are even or odd powered. Okay. Right, where our moments, we're going to use the standard positive negative moments. Conventional positive negative, negative moments. Right, compression top is positive, and compression bottom negative. Right, that's your standard sign convention for these things. Right? Another way people write this is like this, right? Call that positive, not negative. You can sometimes see it written like that. Did you know if you go to Europe, it's the opposite? Cool story, huh? They treat their...
They do everything backwards.
They do everything backwards, yeah. So they flip that sucker upside down for some reason. Because they're... Yeah, that's what they do. Okay. We're better. They probably there's probably some reason why the other way is better, and we just want to be different. So the same thing that everybody just metric, and then we. Because America. You see that Saturday Night Live skit with like Nate Bargatze, right? Talking about that. Yeah, the units and stuff. It's so funny. Except for one thing he gets wrong is he says we have no unit for kips, but we do for 1,000 pounds. We do. Us nerdy engineers.
Which we just stole their kilo.
Yeah.
Kilopounds.
Yeah. So then the other thing that comes out of this, which is, again, really nice we stick with this, if you get an answer that is positive, right? If you're looking at stresses and you get an answer that's positive, that means it's in tension. If you get something that's negative, it means in compression. Okay? Let me put an and. Right? Which is really nice. It's pure. It's pure. If you stick to this, it's pure. The problem's going to be, and we're going to see this, and you're going to run into this in your homework. We're going to stick to this nice sign convention, and we're going to get stresses that are negative, and it's going to be beautiful. But then you're going to be looking up allowable stresses in ACI, and ACI treats everything as positive at all times, right? Everything. And so you're just going to be really careful. If you're getting a value from ACI and it says, oh, it's 0.6 F prime C is what we put in our allowable stress, when you put it into your equations, make sure that goes in as a negative 0.6 F prime C, because it doesn't stick to any kind of sign convention. ACI does what it wants to do. The brotherhood. You just have to know everything is positive, and you just need to know, is it in compression or is it in tension and stuff like that. Okay, so let's do an example with the beam above, just so you can see it at play and see the power of this. Example with beam above. Assume it is loaded with moment of 1,200 kip feet. What are stresses at top and bottom? Right? It's a very simple one. Just given that beam up there, right? What are the stresses at the top and bottom? Okay. So when we go to solve this, one of the first things we have to do is calc I and CGC. Good news, I'm just going to give it to you. Oh, and A. Eventually, you're going to need A. For when we do a full-on calculation or like a full-on design of this, A is going to play in. Right now, A isn't going to play in. Okay? And so I'll tell you what they are. The CGC for this. If you're looking for something to do, you could do that. You could calculate this yourself. It'd be a fun activity today to calculate if you could figure out that the CGC should be 16 inches from the bottom. Right? And the I for this is equal to 12,800 inches to the fourth. I said A doesn't play in. We don't need A. Okay. So those are kind of given to us in this problem. But if you're looking for something to do, you could figure out what that I is. So it's 16 from the bottom. So this height right here, that right there is 16. inches from the bottom. So I know that. And that's going to play in when we calculate our C's. Okay. The equations that we're going to have to use for this, or that we're going to use for these, right? There's no pre-stressing at this point, so it's just going to be simple elastic analysis. My F is just going to be equal to my over I, right? Which is equal to, right? Sometimes it just get thrown in there, it's MC over I, which is also M over S, right? Where S is equal to I over C. And just refamiliarize yourself from this. Okay. This S right here, everybody know what S is called? Yeah, but you gotta be elastic section modulus. Look at you guys knowing your stuff. That's steel. You guys use steel a lot, right? We use Z, the plastic section modulus.
In wood.
In wood. All wood. That's all elastic.
Calculated and then,
Yeah. Okay, so let's do the bottom first. All right, and we'll use our naming mechanism here, or our numbering mechanism, or sign convention, I should say. All right, bottom. Right, so bottom is going to be S1. That's going to be equal to I over C1. So that's going to be equal to 12,800 divided by 16, right? That's the distance so that's the distance from the CGC down to the extreme fiber that we're dealing with, and at the very bottom, that's going to be 16, right? And so this is going to be a positive 800 inches to the third. Okay, now let's do top. Get our section properties for the top. That'll be S2, right? And that's going to be I over C2, right? Which is going to be the same 12,800. And then we divide by C2. C2 is the distance from the CGC to the top, right? So it's going to be this distance, right? So then the overall height's 24, so it's going to be 24 minus 16, whatever that is, okay? Whatever that is. Give a calculator out. Is it going to be 8? Negative 8, because we're going up, right? Negative 8. Right, so this would be negative 1,600 inches to the third. And so it carries its sign. We don't drop that sign. Okay. So bottom is positive 800 inches to the third. Top is negative 1,600. Okay. And then we calculate our stresses. F1, the stresses at the bottom, is equal to M over S1, which would be 1,200. Kip feet or kip inches? Kip feet? Kip feet. Maybe I meant kip inches. I meant kip inches. I wasn't done yet. Connor. Kip inches. Because I didn't do unit conversion down here, so we'll make sure this is the right units. Right? 1,200 over 800. So that equals 1.5 KSI. Right? And then F2 equals M over S2, which is equal to 1,200 divided by negative 1,600. That would be equal to negative 0.75 KSI. Okay, and you can see there, right? I guess the whole point of this, right, is the answer here comes out to be positive, right? Up at the top, or at the bottom comes out to be positive. So this says the bottom is in tension, right? And the top ends up being negative, so that ends up being in compression. So it's kind of nice, right? And this is very simple, right? We just applied one load to it. I know that it's supposed to be compression at the top and tension down at the bottom. I knew that. I can use my brain for that. I know that I see this. But we get really complicated. We have a pre-stressing stresses. You're going to have this tendon that's changing location along the length, right? Like this. And so some places your beam is going to be tension at the top, compression at the bottom. Other places it's going to be the opposite, right? And so trying to keep track of all of those and making sure you're within limits ends up being pretty complicated. So this sign convention is actually really helpful for that. Okay, we're working our way up. Foreshadowing. We're gonna have these plots way out there. All right, these are my stresses. These are my plots. So this is a beam that has a tendon that changes length. This is like homework 2 that you're going to be doing this. But we're going to have these tendons that are changing location along the length of this thing. It's actually a draped section that looks like this. This is where the tendon's at as it goes along. And we're going to calculate the stresses under different loading conditions and make sure they're within the limits. The limits in this case are the blue and the red down here. And if you ever have these lines cross these limits, then it means you've run into problems. And you can see this in some cases, right, they switch, right, where it's, they're the opposite. They have compression top, tension bottom, and they kind of flip depending on where you're at on your beam, and they vary. And so these are really helpful ways of looking at these things. And these sign conventions will make our lives a lot easier. Otherwise, you have to have multiple equations floating around. Compression, everything turns out to be positive, and you have to be thinking like, well, even though it's positive, is it tension, is it compression? You have to keep track of that. The sign convention, you don't have to do it. It just takes care of all of that for you. It's actually really clever. Kudos to Stanton for coming up with it. They don't have this in conventional books. Cool. Everybody all right with that? All right, so we're just going to stick to that. Assumptions for analysis. So let's actually dive in. Let's come up with these equations, right, that we're going to use. They're really, like I said, we already kind of discussed what they're going to look like, but let's actually define them, right? So we're going to do some assumptions. Linear elastic materials. Right. In this, we're underneath elastic analysis, by the way. Under elastic analysis, we're just going to assume everything's linear elastic. Right. When things get overloaded, then things get different. But right now, at the initial part, we're going to deal with this. Right. We're also going to assume plane sections remain plane. Third thing, members remain uncracked. We're actually going to ensure that this happens, but even when it cracks, we still make that assumption for our analysis. We are going to ignore transformed sections. Right? We're going to ignore effect steel has on I. You might remember back to mechanics of materials, if you had two different types of materials, maybe you did in timber. Did you ever put like a steel plate on the timber beam to like strengthen it? Anyways, if you have two different materials that you bring together and you want them to act as one, there's a thing that you do transform sections. You remember this, right? You have to you pretend, well, we're going to do it because later on we're going to have a type of concrete for a beam, and then it's going to have a deck on top of it that's a different strength concrete, and we're going to have to use transform sections to deal with it. But theoretically, in this elastic analysis, you would need to take into consideration that steel has a different stiffness than concrete. And because of that, you have to make some adjustments. And that's where this transform sections. And if you just to refresh your memory, right, if we had, we've got this thing like this, and you got the steel in it. What you do is you transform it, and then you pretend that the steel is, you pretend your section does something like this. Uh-oh. It goes out, and then down, and then out, and then back down. You remember doing something like this? This might be going way back for some of you. Remember that? Yeah, remember that? Yeah, you have this new width, and then you change your eye based on that, and then you calculate it, and then you calculate the stresses, and then you have to transform them back. All of that, you don't do it, okay? At the very end of the semester, or end of this topic, I come back and say, well, what if we didn't make that assumption? I'll show you that it doesn't make hardly any difference if you took that into consideration. We're going to assume superposition. If it's linear elastic, this stands anyway, but it's worth pointing out that superposition. So you could look at just the dead loads and just the pre-stressing forces and just the live loads and just see what it does, and then you add them all together afterwards. That's what superposition is. You could break it up into different like loading conditions and add them all together afterwards, and you get the same answer. External moment does not change pre-stressing force. It does, but we ignore it, right? So what am I saying here? I'm saying that if we go back up to this offset tendon, right? This offset tendon. I got an offset right here. You can imagine if I apply a load down to this thing, it's going to bend down. When it bends down, what happens to this steel down here? Stretches, right? What happens to steel when it stretches? More forces, right? We ignore that, which is interesting, right? Because it's like, oh, because this is pre-stress. It turns out it's very little. That how much it changes when it bends is very little compared to how much we stretched it originally. So we stretched it almost to 270 KSI, and then when you apply a little load, it just makes it move just a little bit. It doesn't actually affect the overall load very much. But it's something that when I first learned this, it always threw me off a little bit. It's like, why? It does elongate when you bend it, and so the pre-stressing forces will go up, but we ignore it. Okay. 3 minutes. Yeah, there's a lot of. Oh yeah, I got this. This is what I did here. I said, oh yeah, like we've stressed it. This is tied to this one. We've stressed it here originally, right? We've stretched it to there, like almost to the end. And when you bend it a little bit, it goes from there to like here, right? And so the stress is barely changed because of that, right? One, it's out in the region where it's starting to bend over a little bit. And then two, it's just a very little change in display. So it doesn't affect the pre-stressing forces hardly at all. Okay. All right, so we're going to do the very first one. I think we get through part of this in the next couple minutes here. We're going to start out with the concentric pre-stressing, just to ease into this concept of eccentric. We already kind of discussed this briefly in passing. So when we have a concentric loading, we're going to have a big pre-stressing force coming in like this. And I've used the term FP before. This is what I mean by FP. It's the total force coming from the pre-stressing, right? It's going to be the area of the pre-stressing multiplied by the stress in the pre-stressing will give us the total pre-stressing force. That's what I mean by FP. And depending on if we have, what condition we're in, it's either going to be FPE that has the losses in it or FPI before the losses, right? But there is a big pre-stressing force that's coming in right there. And then we're also going to apply an external moment to these things, right? This sucker is going to have both of these things, M external. Okay. And then this is where superposition comes in. I can look to see what does this do to the stresses, and then what does this do to the stresses, and add the two together. That means that's the whole superposition stuff. So pre-stress only, we talked about this before. The forces are going to look like this. We got a big FP coming in. FP coming in like this. And then the concrete's going to push back this direction. We call that FC. Right, and we're trying to calculate the stresses in the concrete. So what we really care about is this FC, and they line up with each other, right? FC and FP line up with each other just like that. And then they obviously are related to each other, right? FP is equal to negative FC because they're acting equal and opposite to each other, right? And then that's going to cause stresses in our concrete that are just going to be uniform like this. Right? And these stresses, we mentioned before, are just going to be FC over AC, or they're going to be negative FP over AC. Right? Where AC is the area of the concrete. Right? It's concentric, everything lines up. It's just going to be that negative FP over AC. Because what we're going to go into these equations with is what FP is. right? And then calculating the stresses. The reason that's negative, right, is because my stress, another way to look at it, is this stress in my concrete is in compression at this point, and negative is compression, right? So we want this term to be a negative value, and it's going to be the negative of our pre-stressing force divided by the area of our concrete. Okay? And then what we'll do next time is we'll look to see what the external moment does. That's just going to be my over I, right? And then we'll add the two together. Then we'll go on and we'll do a little slightly more complicated where we have this thing offset. Is yours filled in? It's not? Okay. I don't know why my skeleton notes have it.